All right, let's go ahead and get started. I do want to welcome you to this worksheet. This is Gas Laws Part 1. If you don't have a calculator, go ahead and pause the video because we will be needing one, and we will get started. So let's start with a law called Dalton's Law, or more accurately, I suppose, called Dalton's Law of Partial Pressures. What do we mean by Dalton's Law? Well, what Dalton's Law states is that when we have a container that has multiple gases, that the sum of those gases is equal to the total pressure in the container. In other words, the total pressure is equal to the pressure of the individual gases combined. That's Dalton's law of pressures. So let's take a look at this problem right here. Number 1 says a sample of hydrogen is collected in a flask over water. Now let's take a look at what that might look like. And on the left, we see a container that has, let's say there's hydrochloric acid in this container, and I drop a small amount of magnesium metal. So we now know that from our studies of acids and bases that when we place magnesium or any metal into hydrochloric acid or any strong metal or strong acid, we're going to produce hydrogen gas. So we can collect that hydrogen gas. What we can do is we can place like a rubber tube into the liquid, and on that we'll place a glass column, and we'll submerge that column in another container that has water in it, and we'll slowly bubble the hydrogen gas through the water. So what's going to happen is that eventually, because this is a closed container on the right hand side, what's going to happen is eventually that closed container is going to be filled with hydrogen, and the little red dots that you see are the hydrogen molecules or the hydrogen gas particles that are in the container above the water. But another pressure that we must consider is the vapor pressure of the water itself. If we're bubbling the hydrogen gas through the water itself contains water vapor, or water vapor will be produced by the water. And what's going to happen then is that water vapor is going to have its own pressure. So if we want to know the total pressure involved, what we're going to have to do is we're going to have to sum up or add up the pressure exerted by the hydrogen gas and the pressure exerted by the water. So how might we do that? Well, here's the formula that we're going to use. Dalton's law states that the total pressure is equal to the pressure of the hydrogen gas plus the vapor pressure exerted by the water. So total pressure is equal to 736 torr plus 22 torr. That's equal to 758 torr total. So the question was, what's the total pressure in the container? That's this container here. What's the total pressure? It's equal to the sum of the vapor pressure of the water and the hydrogen itself. So that would be 758 torr for number 1. Let's look at number 2. Number 2 says, what will be the volume of a balloon at 98 kilopascals if its volume is 9.65 liters at 235 kilopascals? Now what we're going to have to do this time is take a look at another law called Boyle's law. Boyle's law is the relationship between pressure and volume, and we'll find that it is an inverse relationship. That pressure is inversely related to volume. And we can make this statement as Boyle did, which is P1V1 is equal to P2V2. Now if we solve for V2, that's what we're looking for in this problem, we get P1V1, pressure 1 times volume 1, the pressure in the first situation, divided by the pressure in the second situation. So that's V2. Now let's just plug in. We have 235 kilopascals times 9.65 liters divided by 98 kilopascals. To the correct number of significant digits, when we do that multiplication and then division, we get 23 liters. Number 2 is 23 liters. So that'll complete the second problem for us. Let's go on to number 3. Number 3 says this. What pressure is required to reduce the volume of gases in a car cylinder from 48 cubic centimeters at 102 kilopascals to 5.2 cubic centimeters? So what we're going to do is we're going to use Boyle's law, but we're going to try to figure out a reasonable answer. In other words, we want to know in advance what's going to happen in the second situation. Well, remember that Boyle's law is an inverse relationship. As long as temperature remains constant, pressure times volume is equal to pressure times volume. In other words, as the pressure increases, the volume decreases. Well, that makes sense in terms of what a gas is. Remember, a gas is particles, but consists mostly of empty space. So if we compress those particles together, we're going to get a smaller volume. So in this case, we want to reduce the volume, and we want to know what's going to happen to the pressure. So keep in mind the original pressure was 102 kilopascals. So we're looking for something above 102 kilopascals since the volume is being reduced. So let's set up our equation. We're looking for P2. P2 is equal to P1 V1 divided by V2. Now let's plug in. P1 is 102 kilopascals times V1, which is 48 cubic centimeters, and we're going to divide that by 5.2 cubic centimeters. When we do that math to the correct number of significant digits, which is 2 significant digits, we get 940 kilopascals, and that'll do it for the first one. Let's look at number 4. It says, or for the third one, I'm sorry. Let's look at number 4. It says an exhaled air bubble underwater at 290 kilopascals has a volume of 18.9 milliliters. What will be its volume at the water surface where the pressure is 104 kilopascals? And why must the diver exhale during the ascent? Remember, again, the inverse relationship between the pressure and the volume. Now, temperature, remember, is remaining constant throughout these Boyle's Law problems. We're going to make that assumption for now. But Boyle's Law says that P1 V1 is equal to P2 V2. So V2 then is equal to P1 V1 divided by P2. So let's plug in. V2 is equal to 290 kilopascals times V1, which is 18.9 milliliters, divided by 104 kilopascals. So when we plug those numbers in, do the calculations, we get to the correct number of significant digits again, 52.7 milliliters. Now let's take a look at what's happening as the diver ascends. We see that the volume of the bubble was originally 18.9 milliliters. That was the original volume. Now it's 52.7 milliliters. So obviously the bubble has expanded as it's gone from the depths to the surface. Well, let's take a look at what's happening in the diver's lungs. So we can imagine residual volume of gas, or air in this case, in the diver's lungs. What's going to happen to that gas as the diver ascends? Well, as the diver goes more and more into more and more shallow water, in other words, ascends, the volume of air in his lungs is going to expand. So he must release air slowly as he rises to the surface, so that air does not explode, obviously, in his lungs. So for that reason, it is necessary for that diver to exhale as he's ascending, so that the volume of the air in his lungs does not simply overwhelm his lung capacity and cause him to die. So that's number 4. Let's look at number 5. It says a diver's tank contains helium at 924 psi, nitrogen at 1456 psi, and oxygen. We're not told what the psi of the oxygen is. It simply says the total pressure is 2,803 psi. What partial pressure is exerted by the oxygen? Well, obviously we've got a number of different gases here. We've got a total pressure. This is a Dalton's law problem. So we're going to say total pressure is equal to the pressure of the hydrogen plus the pressure of the nitrogen gas plus pressure of oxygen gas. So the partial pressure of the oxygen then is the total pressure, which is 2,803 psi, minus the sum of the partial pressures that have been provided. That is the hydrogen and the nitrogen. So what's left is the oxygen, so that subtraction will give us the partial pressure of the oxygen. It's 423 psi, and we're done with number 5. Let's go to the 6th and final question. It says a gas sample has a volume of 3.00 cubic decimeters at 101 kilopascals. What will be the volume of the pressure? What will be the volume if the pressure is reduced to 14.2 kilopascals? Well, no mention is made of a temperature change, so we're going to stick with Boyle's Law on this one. It's P1 V1 is equal to P2 V2. So remember, it's an inverse relationship. As pressure increases, volume decreases. Let's solve for V2. So the expression is V2 is equal to P1 V1 divided by P2. P1 V1 divided by P2. So now what we've got then is V2 is equal to, let's plug in. Let's see, it looks like I've switched these two. It doesn't matter. The P1 and the V1 are multiplied together. So we're going to say 3.00 decimeters cubed times 101 kilopascals, and we're going to divide that by 14.2 kilopascals. So V2 then is equal to, when we do the multiplication on top and then divide by 14.2, 2.13 cubic decimeters. That'll do it for number 6. That'll do it for this worksheet. I'll see you on the next one. Thanks. Bye-bye.